Okay, guys, so we are going to start our unit today on dynamics, which is a forces unit. And we're going to start our discussion today with Newton's third law and force schemas. But before we get to any of that, we're going to look at the definition for what a force is. Okay, so a force is an interaction between two items that results in a push or a pull. It could be an interaction between two objects, or it could be an interaction between an object and a field, or even two fields. Okay, and so you have, that's why it says items. It's kind of a vague term because it depends on the type of interaction you're talking about. Sometimes you're looking at two objects that physically collide with each other and therefore push on one another. But sometimes you're talking about an interaction between your mass and Earth's gravitational field, for example. Forces, when we talk about them, are vector quantities, which means that they have both a magnitude and a direction, and thus we can represent them with vectors or arrows in our diagrams. And then they're measured in units called newtons, okay, which is abbreviated as a capital letter N. So again, forces are interactions between two items that result in a push or a pull. Could be two objects or an object in a field. They are vector quantities and they are measured in newtons. And so you can see an example of an interaction between two objects in the animation below, where you have a baseball and a bat colliding, and of course you have an interaction between those two objects there, and it does involve a push between the two of them. So we're going to be looking at scenarios like that today, where you might say something like the bat pushes the baseball forward. Probably wouldn't use the word pushes there, but technically that is an accurate statement as well. You'd probably say hits the ball forward, but it is a push from the bat to the ball. Okay, but it's also a push from the ball to the bat, and we're going to be looking at that today as well. Okay, make a note that an object cannot exert a force on itself. Okay, you can't lift yourself, for example. You can't exert a force on yourself. Now, if you talk about like the mechanics of you like moving and lifting your leg, then obviously there are parts within your muscles and stuff within your body, and yes, those can exert forces on other things, but you can't exert a force on yourself, nor can any object do that. Okay, there are two main types of forces that we're going to be talking about. These two main groups are called contact forces and field forces. A contact force, as the name suggests, involves contact or touching of two objects. So it says the forces exist between an object in contact with another object, forces between objects that touch, like the baseball and the bat that we saw on the first slide. Field forces, the second main group of forces, are forces that exist between objects that are not touching each other. And these are also called non-contact forces or at-a-distance forces because they will pull on something or push on something at a distance instead of having to physically touch that object. Can you guys think of any examples of something that would be a field force?
Gravity.
Sure. Magnets, gravity, those are the two that I was expecting you guys to come up with. Okay, those forces act at a distance. You can use one magnet to repel another or to attract another without them actually physically touching. And the same thing is obviously true of gravity. The Earth and the Moon, for example, are obviously not touching one another, and yet we know that the Moon remains in orbit around the Earth because of the gravitational field, Earth's gravitational field pulling on it, and the interaction of those two masses. But that's due to a field. They're not touching. Okay, forces between objects that are touching. These are just some examples of different types of contact forces. If you want to jot some of these down, you can. You've probably heard of some of them, maybe not all of them, but friction or frictional force, tension force, normal force, air resistance, applied force, spring force, would all be examples of contact forces. Okay, so you have things like friction when you have one object that is sliding or rolling over another object and the two surfaces are in contact. Tension, and we're going to go into more details later on what each of these is, but you're going to have tension in something like a rope or a cable or a string. Normal force is one that you're actually very familiar with, even though you may not be familiar with the term. Right now you're sitting in a chair, and the chair is supporting your weight, and that support force from the surface is called the normal force. Okay, it's also the force that is supporting your computer if it's on your desk, or your notebook, or whatever. From a surface, the support force is called the normal force. We'll go into more details later about some specifics, but these are just some examples of contact forces. I've already asked you the question, what about non-contact forces? And again, you guys came up with the two examples that I would have expected you to, and that is magnets and the force of gravity, which of course is causing these guys to fall out of their kayak, since they apparently have, I don't know why they're trying to stand in a kayak, honestly, but terrible balance on top of that. Okay, so these are your field forces. And again, you got the first one, gravitational force, which, by the way, is responsible for your weight. And so whenever we talk about gravitational force, it is also the weight of an object, because the field, in this case, the gravitational field of the Earth pulling on your mass gives you your weight. The second one, electromagnetic forces, would include electrical or electrostatic forces, magnetic forces, or of course just electromagnetic forces, and when you're looking at the two together. And then strong force and weak force, I'm just mentioning them. We are not going to talk about them, but they have to do with the composition of the atom, like the forces that hold the nucleus together, for example. Okay, but you have 4 different field forces. These 4 forces are called the 4 fundamental forces of the universe. If you want to write that down, you can. But whenever we talk about the 4 fundamental forces, they are gravitational, electromagnetic, strong, and weak. Again, it's really just in this class, it's really just the first one that we talk about. And if you take AP Physics 2, you'll get into the second one for sure. I can't remember if y'all get into the others in there. I think AP Chem, you get into strong and weak. All right, so defining forces. How can you detect if a force is acting on you? You can determine that based on its influence on an object's motion. Okay, if there's a force acting on an object, you could see a change in the motion of that object. You might see that as speeding up, slowing down, or turning. But right now, there are forces acting on you, and nobody in here, so far as I can see, is speeding up, slowing down, or turning. And so there are always forces present. Okay, so it's not just whenever we see a change in its motion, but they're really obvious when we see a change in the motion. But forces are acting on you right now. Maybe it's gravity. It is, for the record. That's definitely acting on you. Earth's gravitational field is pulling you down. It's the upward force from your chair, which I mentioned a minute ago is the normal force. Those are acting on you right now. Friction sometimes whenever you're moving anyway. But again, there are always forces present. It's just that they may not always cause a change in your motion, but they can. And if you do see a change in the motion of an object, you know that there is some net force in that example, in that scenario. Okay, so again, Newton's third law. I told you that was going to be the focus of our notes today. So because we define forces as interactions between 2 objects, Isaac Newton referred to these forces as action-reaction force pairs. Newton's third law describes the nature of forces in an interaction between 2 objects, stating, in the red part, that's Newton's third law. I would write it down if I were you. It's something you've definitely heard before. It says, for every action, there is an equal and opposite reaction. Okay, so when we talk about Newton's third law, it states, for every action, there is an equal and opposite reaction. And if you think back to the way that we defined a force on the first slide, we said it was an interaction between 2 items. Okay, and that interaction between 2 items, you're going to have equal forces on each of those objects or items, okay, in opposite directions. It's going to constitute a force pair, an action-reaction force pair. Okay, what this means is, if you want to write down this part too, for every action there's an equal and opposite reaction tells us that a force that's exerted on one object will cause a force of equal magnitude but opposite direction on the other object in the interaction. So like on my very first slide, we talked about a ball and a bat. And I said that the bat hits the ball forward. Well, the ball also hits the bat in the opposite direction. So if the bat pushes the ball forward, the ball pushes the bat backwards. That would make up your action-reaction force pair, an equal and opposite reaction. And that's what this says, that those forces are equal to each other, equal in magnitude but opposite in direction. So Newton's third law, there are a lot of misconceptions surrounding how to interpret this, because students will see a scenario like the bat and the baseball, and I'll ask you a question like, which one of these experiences greater amount of force, and then I'll hear a lot of people tell me the baseball, because you look at the scenario, you're like, well, the baseball is flying across the field and the bat's still in the guy's hand. It doesn't matter. There are other forces acting there, but if we focus just on the force between the ball and the bat, they are equal and opposite. That is what Newton's third law says. Okay, so don't fall for a trick question like that. If I ask you which one has a greater force acting on it, you need to tell me that they're the same every time. Now, are there other forces? Sure, because there are other objects involved in that scenario. Okay, but looking at just that force pair that exists between the bat and the ball, those forces are equal and opposite to each other. Okay, and that's the example I was just talking about. So identify the force pair in the following example. Again, the bat pushes the baseball forward. So we could say that there is a force of the bat on the ball. And again, the other half of that force pair would be that if the bat pushes the baseball forward, the baseball pushes the bat backwards. Okay, and so we would say the force of the ball on the bat, and it is in the opposite direction, but they are equal and opposite. Okay, so the positive force, or the forward force of the bat on the ball, is equal to the backward force of the ball on the bat. They're going to have the same magnitude, opposite direction. That would constitute a force pair. Okay, so let's see if we can write out some interaction force pairs. So I have an example here that says a book is at rest on a table. And if you're trying to write out your force pairs or identify what they are, your first step is simply to identify two objects in the interaction. So in this case, I'm just going to go with the book and the table. Could I have picked other things? Sure. There's a floor. There's the earth that these are all on. Okay, but for this example, we're going to pick two of the objects. And it's probably going to be pretty clear most of the time which two you're going to be looking at based on how the question is worded. But here I'm just looking at the book and the table. The second step after you've identified the objects is to describe the push, and it should say or pull, but because it could be a pull. Describe the push or pull on one of the objects and include a directional adjective. So for example, the book pushes down on the table. So I have my two objects, book, table. I have a directional adjective that describes the push. It's pushing down. Okay, so there's my direction. But the book pushes down on the table. Okay, the other half of that force pair, for that part, you'll describe the push on the other object and include a directional adjective. Again, when you write it out, just switch the position of the two nouns and switch the direction. If the book pushes down on the table, we could also say the table pushes up on the book. Same two objects, book and table, okay, different direction. And I wrote it in the other order. The nouns switched places. So that's just a general rule, but this is pretty straightforward. I think y'all could probably come up with this on your own. So this would be an example of an interaction force pair. The book pushes down on the table pushes up on the book. If I asked you which of those forces were greater, you would tell me that they are equal and opposite. Okay, that's what it means whenever we're talking about force pair. Are there any other objects involved in this scenario? Sure, the earth. It's an obvious one. I heard somebody say gravity. Not an object, but right idea. The earth has a gravitational field. That's where that gravity is coming from. And sure, we could include lots of other things, but the earth is the most obvious one. Okay, yes, the earth. I could include that too. Okay, and then I would have to start identifying force pairs between the earth and the book and the earth and the table. Okay, but it wouldn't be part of that force pair between the table and the book. Okay, now, in order to help us see these force pairs easier, we can use a tool called a force schema. Okay, so a force schema will help you to see force pairs. It shows only the objects interacting, represented by labeled circles. In this example, there are three. I have the book, the table, and the earth. Okay, and so if I wanted to show the forces that exist between them, I'm going to use a double-sided arrow. If you want, you can draw two arrows, one of them pointing, up and one down, or left, right, whatever. Okay, you don't have to do a double-sided one. You could have one arrow pointing from the book to the table and a second arrow pointing from the table to the book, and that would be fine too. Okay, but I did mine as double-sided arrows because I just think it's easier to draw it that way. But each of these double-sided arrows represents a force pair. Okay, this one that's in blue up here is the force pair that we just defined a moment ago, where we said that the book pushes down on the table and the table pushes up on the book. That's represented by this force pair, this blue double-sided arrow here. Okay, so if we wanted to label our force pairs, let's put our schema back. This is the one that we just talked about. The book pushes down on the table pushes up on the book. That is this force pair. I could also talk about the force pair that exists right here between the table and the earth. And I know that Earth's gravitational field is going to pull down on anything with mass. Okay? It pulls on you, it pulls on the table, it pulls on the book, it pulls on everything that is on or near Earth's surface, okay, or in its vicinity. Okay, and so we have the table pulls up on the earth and the earth pulls down on the table. That is a force pair. The earth pulling down on the table makes sense to you guys, hopefully pretty logically, because that is, again, the earth pulling down on you as well. That's why you have that acceleration downward. The table would too. If it was in free fall, if you dropped a table out of a skyscraper, yes, it's going to accelerate downward, okay, because the earth has that gravitational field, that pull on it. Okay, but the other half of that force pair is the table pulls up on the earth. Any two objects with mass will have a force of gravitational attraction between them, and it's really weird to think about, but you do too. The earth pulls down on you, you pull up on the earth, and that is the other half of that force pair, and that is a force pair. Those forces are equal and opposite. You pull on the earth with the same force that the earth pulls on you with. Okay, and we're going to get more into that later and talk about why we don't notice any real change or effect of our pull on the earth. Okay, whereas on the other hand, the earth's pull on us, we definitely can see that. But we'll get into that more later. Right now, we're just looking at the force pairs. So that red one is the table pulls up on the earth pulls down on the table. The last one, that green one, the earth pulls down on the book. Again, that's the book's gravitation. The earth's pull on that book gives the book its weight. Okay, and the book pulls up on the earth, and that's the other half of that force pair. So again, when you draw a schema, you can see each part of it, okay, between each of those two objects. This is what I was just talking about.
All right, watch this.
Silly clip.
What is this? What is this, some kind of gag? No, that's orbit. Huh? You have your own gravitational pull. Oh, that's a bunch of crap. Now back to the Three Stooges.
So I know it's really silly and it's a really short clip, but in that episode, Peter has gained so much mass that he now has a greater gravitational field. Obviously exaggerated, that can't happen. But any objects with mass have a great gravitational field. Whenever I talk about that, I always think of that image from that episode. But again, that's a force pair. The earth pulls down on you, you pull up on the earth. Now, you're not going to have, whenever you talk about like these objects orbiting him, you don't have enough mass for that. We'll get into that later. But again, it may help you remember it. I don't know.
Thank you.
You're welcome. All right, so again, those force pairs are kind of lengthy to write out. So here is another way that you can write them. Okay, so you can write it like this. Force of table on book equals force of book on table. That is how you read this. And you'll notice that this one is an upward force. The force of the table is pushing up on the book. The force of the book is pushing down on the table. That's why the negative sign is here. I went ahead and defined up as my positive direction and down as my negative one. Okay, so I'm showing here that these forces are equal and opposite to each other. I could do the same thing over here and say the force of the table pulling up on the earth is equal to the force of the earth pulling down on the table. Again, they're going to be equal in magnitude. The last one, of course, the force of the book pulling up on the earth is equal to the force of the earth pulling down on the book. Okay, so again, equal in magnitude, opposite in direction. But that is another way that you can write out your force pairs. Table on earth, earth on table. Writing it like that's a little shorter than writing it out as a sentence. Okay, a little bit shorter, not a lot shorter. You could use just the first letter as long as they're unique letters and it's an obvious label and it would be okay. I'm fine with that. All right, for the rest of the class period today, you're going to be working on playlist 1 for Unit 3. It is due on Monday. It only has 2 things in it, 1 task option and 1 checkpoint. So it's not a lot of stuff to do, and it's not due, of course, until Monday night. But you can start on it for the rest of the class period today and work on that worksheet. It's up at the front of the room. And then you can complete it on Monday. The second thing that's up there, guys, real quick, your bump assignment for marking period 2 is in Schoology. Check the Schoology course to find it.